Right, so we'll just make a start now. I've got one more presentation I want to do, and that is the ISP network design one. It's not really anything to do with BGP or IPv6 or that, but I still think it's useful, because quite a few of you are starting off new networks, how to design things, how to interconnect, what to do, and so forth. So I thought it would be useful. Well, I was asked to do this, so I thought it would be useful to put it into the workshop, just to make it part of what we're going to cover. So it's not too long, but we'll just quickly go through it so that you've got some good ideas for how to do your infrastructure design. And it backs up some of the principles that we've been talking about during the workshop labs, when we look at some of the BGP design and so forth. So these are the topics. We've covered some of them already, but we'll look at POP topologies and design, backbone design. Addressing we've done. We've covered that a couple of times, but I'll quickly go through it. Routing protocols we've done as well, but we'll cover that also. Security, it's not a lot being talked about here, it's about security, but I'll show you some of the basic things you want to think about. Out-of-band management is very important. Operational considerations as well. That's like just operating the network, how to do it, what accepted good practices are as well. So this is in the design presentations folder in the handouts that you got. So if you want to follow the slides, you can do so. So the first thing we'll look at is the point of presence design. We've talked about core routers in the first day, high-speed trunk connections, distribution access, bigger networks of distribution, null-sized ones. You have the access routers where you connect your customers to the network. Border routers connect you to other service providers. It's very important that you have a border router in your network, so it's separate from any of your backbone. Service routers, where you do all the hosting and services. And as I said on Monday, some of these functions can be handled by a single router. It's not that you have to go to your vendor and buy all these different routers from the start. You can start with one router, and as that fills up, you can expand it out by another one of the same size and start building a network like that. It will be more scalable and offer better redundancy than trying to just buy a bigger and bigger single box. So these are the general allocation of routers that you get in most ISP networks. Now with the POPs, you want to try and do some type of standardized design. The bigger ISPs will separate the aggregation services according to connection speed, the type of customers. I talked about contention ratio earlier in multi-homing, whether you want to do 2-to-1 for high-value business customers, 6-to-1 for normal business customers, 30-to-1 for consumers. That's typically what ISPs are trying to do. And you also want to bear in mind the security considerations as well. And you want to try and bear those in mind also. Security is a high responsibility for an ISP. And security is not just achieved by putting a firewall in. ISPs don't have firewalls. Right? It's the end sites, the end users that have firewalls. ISPs are about moving packets around, and the security that an ISP does is to make sure that infrastructure is secure. Right, so we start off, we talked about core routers, so we've got the two routers in the core. We've got backbone links to other POPs. So we saw that on Monday. Typical type of design, got the two core routers. If you have other points of presence in your network, then you make sure you have redundant links, not just one. ISP services connected like this. So it could be your DNS, primary, secondary DNS, your mail servers, your mail systems, the news if you have that, FTP, web servers, any other content service type delivery. Put them in their own piece of network. Don't put your mail and your DNS servers on the same LAN as your customer servers. Right? So don't put them on the same place as your customers. Have a dedicated subnet for these. If you have multiple POPs in the backbone, spread your services around the backbone as well, again for redundancy. If you're doing hosted services, data centers and that type of thing, separate LAN. Separate LAN. I mean, how you do this, it can either be a LAN hanging off the core routers, or you can have dedicated data center routers here, which then have all the different hosted LANs sitting behind them. It just depends how big the data center effort is going to be. And then we have the customers. So we've got leased line customers, so how do they connect, whether it's the traditional TDM leased line, or whether it's fiber, or it's point-to-point wireless, or whatever. But that's your leased line aggregation layer sitting in here. So again, it would be a separate business unit perhaps. The bigger networks tend to do that. You might have Metro Ethernet, so again, some parts of the world you have Metro Ethernet. So again, you've got the custom aggregation layer in here, the Metro Ethernet routers connecting into the network core. What else? Border routers, they have a very tight link into the network core. So you've got your border router here. If you've just one POP, you'll have two routers. If you have more than one POP, it's a good idea to have one border here, one border somewhere else. Again, for redundancy, if this POP breaks, then at least you can still carry on running your network from elsewhere. Web caching is always a good idea, whether you do transparent or non-transparent cache. Web caches quite often go at the border network. They can often go down to the customer portion as well, as I'll show you in a few slides. But the web caching, content caching is always a good idea because it saves bandwidth. Network Operations Center, again depending on the ISP size, the bigger ones. NOC has a dedicated connection into the network core. You don't want your NOC to be sitting somewhere in the company office LAN, behind a firewall. Very bad design. Because if something happens with the firewall or the company LAN, you can't run your network. So the Network Operations Center is attached directly to the core of the network. Any issues, the NOC have direct access to the network core. They've got immediate access to the network core. Consumer access, well, the cheaper consumer access, it depends, it can come in different places, connecting directly to the network core, or maybe some other part of the network. But they would all hang off the core as well. So that's the typical type of thing. You go to the really big ISPs, they have different business units running these different functions. They've got different business units running these different functions. The smaller providers, it tends to be just the same people doing everything. But it's still worth thinking along the lines of how this is going to scale in the future. You always want to try and design things to be nice and scalable. Now for the IGP design, using OSPF, for example, you want maybe try one area per POP. You don't need to do this quite so much with ISIS, but try and do aggregation within the IGP if it's possible. Like things like point-to-point link addresses used here, you can aggregate those into IBGP, for example, into the core, rather than having lots and lots of little /30s running around in the backbone. So be careful with your IGP design. For BGP, route reflector. So, again, the two core routers are the route reflectors for all the other routers in the point of presence. Very common design. The two core routers are the route reflectors. That way you can scale IBGP. These two core routers, full BGP mesh with other POPs. Right, the cores and other POPs. But within this POP here, two route reflectors, all the other routers are clients of these route reflectors. And that makes sure that the IBGP will actually scale. Right, so that's pretty much the same thing. Now, the point of presence design. For the type of modules that you have, low-speed customers, so these could be, I don't know if there's still modem dial-up, some people still have this in parts of the world. Low bandwidth, low revenue. You probably have some dedicated access router. In fact, these days the bandwidth is so small, people don't really worry about this. Leased line customer connections, here we're looking at like 2 megabit type speeds. They pay slightly more cost for this, more revenue. You need to be probably a little bit better with how you connect some of these organizations. Broadband, now this can be over DSL, over the copper phone lines. It can be over the cable network, cable TV. It can be wireless, you know, whether it's WiMAX, Wi-Fi, point-to-point, microwave, whatever, it doesn't matter. These are broadband, they tend to be higher bandwidths. Again, they don't pay very much money for this type of access. You have large numbers of them, so you need to think how you're going to connect these into your backbone. You've then got Metro Ethernet. This means you're running fiber or Ethernet to buildings. Some parts of the world, as the ISP puts a router in the basement of a building and then runs Ethernet to every single apartment. So they're the very, very big bandwidths involved. The ISPs are very fast internet. They offer television, IPTV, this type of thing over that type of connectivity. So we're looking at like gigabit Ethernet or even higher with maybe 10 meg or 100 megabits per second into each apartment. So the demands from these types of customers can be very, very big. Point of presence core, you've got 2 dedicated routers, as I mentioned. High-speed interconnect between the 2 of them. Typically, it's your biggest bandwidth connecting the 2 routers because of the transit link through your point of presence. Make sure the core routers only have backbone links. So the core routers tend not to have lots of slots. They tend to be smaller, 4 or 5 slots to carry the interface cards to connect to other parts of the point of presence. Right? They're not big routers. They're fast routers, but they're not physically that big. The main idea is not to touch them. Like you shouldn't need to upgrade them. You shouldn't need to change software, change configuration. The core routers should be very stable. I mean, typically, core routers, ISPs, IAccess, have uptime of about a year. That's a sort of length of time between doing any maintenance work on them. You should not need to touch them. The border network, dedicated border router to other ISPs. So this is the ISP's front door. The border router is actually very, very important. It protects your network from the internet. It protects the internet from your network. It's where all your peering is done, your BGP policy is done, your connecting to other ISPs is done. You may want to do web caching at the edge of your network as well. You may want to do it in the core of the network also. 2 border routers in the backbone is the minimum that you need to give you redundancy. So make sure that you always have the 2 in the network. For the ISP services, so things like DNS, so your DNS cache for your consumers to use, DNS secondary for any domain names you're hosting. News is probably not relevant anymore, but mail, you want POP3, IMAP, mail relay, doing all your antivirus, anti-spam scanning of customer mail, that type of thing. Right, so the mail services are very important. www, There's the server, so your company web server. You maybe want to run web proxies as well, web caches. All these things are good to offer your customers because it keeps web traffic off your international connections and makes the general experience faster for everybody. If you're going to do hosted services, data centers, so things like virtual hosting, virtual web, information content services, you've got business who want to do electronic commerce and so forth, keep it separate from this. Don't let these servers sit on this network. You don't know what these people are doing. They may be a compromised web server. Getting into your ISP services is very bad for you. So you keep them separate. Generally, if you do web hosting, you have one VLAN per customer. That's a typical design today now. So you have the router, big Ethernet interface connecting to an Ethernet switch. Each Ethernet port is on a different VLAN. You're aggregated into the router, and that way you secure each customer from each other and from the internet in general. Don't just have one flat line with every single web server sitting on it. One VLAN per hosted server. You can have up to 4,000 VLANs, so there's quite a lot of scope. Network Operations Center, if you've got multiple sites, is probably worth considering primary and backup locations. This is where you do your network monitoring, your network management, you do all your statistics gathering, your log gathering, where you run things like MRTG, NFSend, NFDump, or Argus peak flow. You do your security monitoring, intrusion detection, remote trigger black hole filtering, all these things. All is run from the NOC. It's actually a very important part of the ISP. Even a small ISP, set aside a small room where you have a few computers, few screens that are available for immediate access to the network. You need direct access to the backbone, but it needs to be secure as well. You don't want people to be able to break into your NOC. You also need an out-of-band management network, which gives you out-of-band access, so access to the console ports of the routers, switches, and other servers. So I'll show you how to do that later. Low-speed access, typically, well, this is PSTN, but here again you can see the sort of design. We have a connection to the core routers. We've got the access network gateway routers here. Right, so we have routers that host the network. This is the whole module part. You have the access servers. You can do all the authentication here. You've got DNS caches, so the DNS resolver. You can have web proxies, web caches. You can do the service selection gateway, service control engine, all these things can all be done this part of the network. Okay? So giving you, well, this is all your consumer, say the analog access like this. Broadband access will look very, very similar. We'll get to it later. But that's the sort of design you want. Try and keep regular small traffic off the backbone. So that's why web caches, local authentication and so on is very important. Medium speed access, so this is your business consumer, business customer links. However you connect them, they're all pretty similar type customers. And same with high speed. You probably put them all into one box, but typically again you've got these routers, the aggregation routers within the network. So the broadband access module could look something like this. It could be the telephone network connecting to the DSLAM, IP, so PPP over Ethernet, connecting to your BRAS, which is just the broadband remote access router. So BRAS typically are normal routers terminating PPP over Ethernet or PPP over ATM connections on here. Connecting into the core, again, we've got web caches, we've got authentication, DNS resolver, that type of thing. Cable system, again, you've got the cable access server here. again connecting into this small part of the POP, and then you have the access routers there connecting you into the core. Some ISPs call this distribution layer. Right? You have the router sitting in here, controls the access between the backbone and the actual broadband module. And again, the idea is to try and give as much access to the, well, content access to this part of the network, trying to isolate it from the actual backbone infrastructure, the core routers. With these access gateway routers or the distribution routers, you can do router-based rate limiting, so you can set limits on what the broadband customers are actually capable of doing on the backbone. It's a nice, easy way of doing it on the router. ISP services, something like this. You've got the Ethernet LAN here. The service network gateway routers. Again, connecting into the core. These routers are very important for protecting your servers from the network. For example, if this is a DNS server, then port 53 is probably all that should be getting through from the outside world. And secure shell. Right? So you use the filtering capability, the packet filtering capability of those routers to protect your services LAN. Same for POP3, mail relay. Mail relay is where all your customers send the outbound email. So an outbound email goes to your mail relay and then out to the world. Customers come to your mail server here to get email. News if you do it. DNS cache is probably useful to have in the network as well. It's a good idea to have several DNS caches scattered around. Probably also put the web cache here also. Make sure the filters here are very, very strong filters so that providers or your customers can only get access to the services they intend to get. The hosted services module is slightly different. Here it's your different customers coming in. As I was saying, they get their own VLAN. So each server has its own VLAN on the Ethernet switch. The VLANs are aggregated on the routers, and that way you secure the access for each customer. Again, only give the customers access to the services they've bought. So if they're going to run a website, they get port 80. Give them secure shell access. Don't let them telnet or use other insecure ways. Like Microsoft remote access and all these things are totally insecure. The only way people should be accessing these servers is through secure shell, SSH. Border module, so again the border routers, connecting to different ISPs, connecting to local exchange point, make sure the router has no default route, no full BGP table, only carry the local routes on here. So the border module could look like that. Network operations center, I pointed to the one router here, connecting to the two cores. You'd have your primary DNS, that's hidden from the world view, that's a very important system. It's where your domain name and all your hosted domain names are kept. Your public secondary name servers are the ones that the world sees as providing all the DNS. All the logs from your routers, capture them here. TACAC server for secure access, so user authentication access to the routers. You don't store usernames and passwords on the routers. We use an external server, or servers, plural, to do that. NetFlow I mentioned as well, NFSend, NFDump, so your NetFlow analyzer goes here also. Or if you buy a commercial system, it can go there too. Out-of-band management network, if your NOC is in the same building as the data center, good idea to have the out-of-band management network connecting to that router. We've got the firewall here. This firewall is connecting the network operations center to the corporate LAN. But quite often the NOC will need to look up the customer database. Customer database, of course, is inside the corporate network. You don't want your billing system and everything to sit on the NOC. Because if somebody breaks into the NOC, then they've got access to all your billing. So you really want to keep the billing system safe there. Right? So the NOC usually has a firewalled connection to your corporate LAN. Or at least that's how we did it. The out-of-band network. So we have a terminal server here. We connect the router consoles to the terminal server. That connects into the NOC on the ISP backbone. Again, NetFlow-enabled routers. You can, if it's in the same data center, you can send all the flow data to the flow information collectors. So if you're using NFDump, NFSend, this is the sort of design you can do. You don't have to run all the flow data export over your public backbone. You can run it on an out-of-band network. Okay. So looking at the backbone design, routed backbone is what's very, very, very common nowadays. Switch backbone is obsolete. ATM frame relay has pretty much disappeared. It's pretty much disappeared now. So routed backbone is what we have. So routers are the infrastructure connecting by a variety of media types. It can be traditional TDM. We can go into optical connections, STM1, STM4. We're starting to see more people using Ethernet, so GigE, 10 GigE, OC768, even 100 gigabit Ethernet is now reasonably readily available for ISPs to connect. Try and standardize the POP design. So if you've got multiple POPs in your network, design them to look the same. Because that way it's easier for them to scale, it's easier for you to understand the network design. ISP essential services are distributed around the backbone. That's important too. If you've got one POP, you can't do it. But as soon as you have more than one POP, distribute the services around. Because if one breaks, you have a backup. Consider having a network operations center and an alternative. So again, if the NOC disappears because the POP disappears or you lose power in the data center, at least you can still run the network from somewhere else. Again, most ISPs will do something like this. And of course, make sure you have redundant backbone links as well. That's very important. So multiple POP, 3-POP backbone, you probably want something like this. You've got 3 points of presence, 2 core routers in each. ISP services here and down there, customer connections in all 3. External connections in POP 1 and POP 2. You've got the backup operations center, you've got the primary one. You get the idea. Try and distribute services around the network. So the backbone links, ATM frame relay has virtually disappeared due to overhead, extra equipment, shared with other customers of the telco. This is not good. It was never really a very good offering because telcos oversold what they had. MPLS has pretty much replaced ATM and frame relay as the telco favorite. So the telcos have adopted MPLS really as the replacement for ATM. The other way of doing it is the leased line of general infrastructure circuit. And this is most popular with the backbone providers. IP over optics, Metro Ethernet, this type of thing. People are using Ethernet, Gig Ethernet, and so forth, even for medium distances. You know, some places I see gigabit Ethernet links 100, 200 kilometers long now being used for ISP backbones because it's the cheapest way of providing the infrastructure. Now the long-range backbone links tend to cost more. It's important to plan for the future, and this means planning at least 2 years ahead. But you need to stay in budget, try and stay reasonably realistic. Because trying to do emergency upgrades because you've run out of capacity can be hugely disruptive to the network. So for long distance, you need to be very ambitious. Try and plan as far ahead as you can. Allow sufficient capacity on alternative paths. Sufficient depends on business strategy. Some ISPs leave as little as 20% overhead. This is really very silly because if a link goes down, the backbone becomes congested. The whole network becomes congested. So this is not a good idea. Typically, leaving sufficient free means having 50% of the external capacity available, which means that if one external link goes down, the other one can take the full load without any loss. So I generally find that 50 or 60% free capacity is a design guide for many ISP backbones. Some ISPs push it to 20%. You can tell by the price of their services. If they are cheaper, then they have less overhead available in the network. So if the network breaks, you're more likely to get serious congestion. Some businesses actually choose 0% overhead. They deliberately run the network congested, and instead they try and buy rate limiters to limit what their customers can do. This is very, very short-sighted. It doesn't scale or grow the internet, and it's just really one of the worst options available. But there are people who do this. They tend to offer very, very cheap services, and the only way they can do it is by having zero redundancy in the network. So 50% is really ideal. Right, so long-distance links, make sure you have the redundancy, go as big capacity as you can. Within the backbone, well, within the metro area, so within the city, it tends to be easier if you've got more than one POP, because it's easy to get local fiber. Or you can lay it yourself, or you can use other types of technologies to link the backbone together. So generally, in all the cities around the world, it's very easy to get big capacity locally. So think big, do things like this, have duplicate links between the different points of presence, and that gives you a very good, solid infrastructure in the network. Okay, upstream connectivity and peering. We've seen this already. I talked about this, was it yesterday? Transit provider gives you access to the other networks, could be local, regional, more usually the whole internet. Transit providers need to be chosen wisely. One doesn't give you redundancy, too many, too difficult to load balance. And as I said yesterday, at least two, no more than three. So the common mistakes I mentioned yesterday, too many transit providers, or you get transit providers but you don't have diversity, because the transit providers use the same satellite or the same submarine cable or the same overland cable and so on. So choose transit providers that have different infrastructure for their networks. Peer as much as you can. It's very important to go and get peering everywhere. Peer with all the local ISPs. Obviously don't peer with your customers, peer with your local ISPs. If there are other ISPs in the region who are not your customers, peer with them. It's much cheaper than paying your transit provider. If there's an internet exchange point, be at it. Right? Internet exchange point doesn't cost anything. All it costs you is the Ethernet port you plug into. You don't pay for traffic, you don't pay for transit. So peering as much as you can is very important. It's how the internet has been built, by peering. I mentioned the common mistakes. Some transit providers talk about exchange points, when in fact it's not an exchange point. It's a transit business. They charge for traffic. Right? If they charge for traffic at an exchange, it is a transit business. It is not an internet exchange point. Also, another mistake, not working hard to get peering. You need to peer as much as you can. I mentioned yesterday, ISPs will, especially from the Middle East, they'll go to Europe, get by transit in London or Frankfurt, and ignore the exchange points that are there. And they say, oh, well, we're happy to pay for all the transit. But if they went to the exchange point, they'd get 50, 60, 70% of the traffic by peering. Transit may be cheaper than peering, but this is very rare. Peering is usually cost you nothing more than the Ethernet port you connect into. Other mistake is ignoring or avoiding competitors because they are competition. Right? They are a valuable peering partner because it makes the local internet experience better for everybody. And it helps grow the local internet economy. So private interconnection, two ISPs agree to interconnect the networks. We've covered this. Right, so the private interconnection can look like that. You've got your peering routers. We run IBGP here, we run IBGP there. This peering router has no default route, doesn't have the full BGP table, it's only got the domestic prefixes inside the ASs. And this peering router is used for all private interconnects. For the public interconnect, where the service provider goes to an exchange point, exchange prefixes, it originates into the routing system. ISP will choose who to peer with. You don't have to peer with everybody at an exchange point. Bilateral peering, it's like doing private interconnect. Multilateral peering, if the exchange point provides a route server, then they provide all the prefixes of everybody who uses the route server. So those are the two that you get. So it's something like this. You've got the ISP network over there. The peering router is at the exchange point, and it peers with other ISPs at the exchange. It runs IBGP with the rest of the backbone and eBGP with ISP peers. It has no default, no full BGP table, only got the domestic prefixes on it by IBGP. So that you need to be careful configuring this router. It's remote from the domestic backbone, don't originate prefixes, as well as not the default or no full BGP table. Need to filter in and out. Don't forget to filter. If you have a second link to the exchange point, do it something like this. Put a second router in, second circuit, going from a different place in your backbone. That way you get redundancy into exchange point, and both these routers can then peer with the ISPs at the exchange. Now, for the upstream transit connection, so two scenarios, transit providers in the locality, which means bandwidth is cheap, so get big capacity. Transit providers a long distance away, undersea cable, satellite, long-haul, cross-country fiber, all these things, the different scenarios. If you've got a local transit provider, connect something like this. Your border router here connects to your local transit provider. This may be an Ethernet, well, I don't know, local wireless, optics, but it could be just across town, across the city. So it's a short distance. You connect to your transit provider's access router, and they give you onward transit to the rest of the internet. Right, so you get the default route or the full BGP table, you do your policies as I discussed before, and you do your packet filtering on the border router as you need. If your transit provider is a long way away, in another country, another continent, other side of the world, then you need to do this. You need to take your border router and move it close to your transit provider. This link is very expensive, and you need to be able to control what runs on that link. So typically you go to the transit provider, either their colo center, or find a data center that's close by, or where they're at, put your router in there, and then get a local connection to the transit provider. You can run IBGP with the rest of ISP1 backbone. You run eBGP with the transit provider AR1, AR2 routers. This is the best thing to do. Put your border router next to your transit provider's backbone. So this is if they're a long way away. And if this is a long haul circuit, as I said, another country, another continent. For example, you're here, if you're connecting to an ISP in Hong Kong, put a router in Hong Kong. Because then this router can control what goes in that link. You can do rate limit, packet filtering, all the rest, and you get best use of that particular connection. This is really, really strongly encouraged. Many, if not most of the bigger ISPs I know will put a router next to the transit provider if that transit provider is a long distance away. These long-haul circuits are very expensive. They're very expensive. If your transit provider is local, you can change the capacity anytime you can, very easily. It's just like a local Ethernet connection. But long-haul, you've got latency, possibility of congestion, buffering issues, and all the rest. The upstream provider uses just a standard access router. So if you plug in a long-haul link, you're putting a lot of pressure on their access router to give you enough buffer space. So this moves the buffering problem away from the transit provider. You do it on your router, and you can make sure you get the best performance of your link. The other thing is, if you're in a remote data center and you don't like your transit provider, you can sign up another one and then disconnect the old one. So it becomes very, very easy to migrate connections between transit providers with no downtime. So if you want to change a transit provider and you just plug into their router, you have to arrange to move your long-haul circuit into another data center. And that will not happen without you losing any packets. That can take days to happen, and that will cause outages on the network. So being in a remote colo gives you huge flexibility for running your network. This is why many ISPs will put a router in the remote colo if your transit provider is distant. Other points to consider, well, you need remote hand support. So if you're going to put a router somewhere overseas, you can't go into an airplane and fly there if there's a problem. So you need to find somebody in the data center, and each data center usually has something, who can plug or unplug cables, power cycle equipment. If you need to upgrade the router, you can send them a new one, and they will swap it. You need people to do things like that. So get arrangement with what's called remote hands, and they can do this basic work for you. You also need a support contract from your equipment vendor. You can't just get equipment there with no support. If the router breaks, you then have to ship it back here to do something by getting it fixed, and that costs money. So get a support contract from the equipment vendor so that they can fix issues with the router or whatever locally. It's actually sensible to consider 2 routers and 2 long-haul links. So do something like this. So let the transit provider have 2 routers and 2 links there. So rather than upgrading one link to twice the capacity, get another link of the same capacity, and then you can load balance on the 2 of them. 2 independent circuits, and even consider connecting to an internet exchange point. Yes, you get the transit provider, but most data centers have an ISP as well. So you can connect to the exchange point also and get free peering. So summary of this, private interconnect, simple private peering. We've looked at the design needed for public interconnects. Put the router at the colo, at the exchange point. Local transit provider, simple upstream connection. Long distance transit provider, put the router in the remote colo, remote data center, and connect to the transit provider there. And also consider going to an exchange point there. Now, the IP addressing, we've seen this all before, so I've talked about this already. Don't use private address for addressing the backbone, use public addressing, otherwise it just makes it really hard to run your network. The well-known problems, I've listed all the problems of trying to use private addresses for the backbone. It's really a bad idea, so don't do it. If you want to do it, make sure you have a NAT on the edge of your network so you can do the translation. So what else? Infrastructure security is not improved by using private addressing. You can still be attacked from inside or by your customers or by reflection techniques. It's very easy to attack through a NAT. It makes troubleshooting harder because you have no internet view from the routers. Other ISPs cannot distinguish between down and broken. Path MTU discovery can be broken as well, So the summary, always use global routable IP addressing for your infrastructure. That's very important for an ISP. So do the address planning. I mentioned this already. Address block for the router loopbacks, address block for the infrastructure point-to-point links. Similar policies for V6, we've covered all these already. Customer assigned address space according to needs for V4. V6, they get a 48 or a 56 or a 60 or a 64 or whatever. Put the customers into IBGP, not OSPF. So I looked at the address plans. We've done this before in the labs. Phase 2, well, V6, you're likely to get an adjacent one. V4, it's all gone, so this doesn't work anymore. What was the difference between these two? Don't know. Right, so registries will usually allocate the next block to be contiguous. But, well, this is not going to happen for V4 anymore. V6, it still will do. Documentation is quite important, so document all your address allocations. I talked about the different tools for documenting addresses the other day. Whether it's a flat text file or a spreadsheet or one of these online tools that you can use, or use the routing registry, it's entirely up to you, but please document the address allocations. For routing protocols, we have IGP, carrying infrastructure addresses point-to-point links. So we have OSPF and ISIs. For EGP, we've got the exterior gateway protocol, so BGP version 4. We use ISIs to scale the backbone. All the point-to-point links let the routers talk to each other. And we need BGP so that we can scale to the internet and give us policy between different autonomous systems. So that's why we have BGP. As I showed you on Monday, comparing the two, automatic neighbor discovery for ISIs, specifically configure the peers for BGP. You can trust your IGP routers, but here you're connecting outside the network. Prefixes go to all IGP routers, whereas BGP, we set administrative boundaries. Right, so ISIs carries the infrastructure addresses only. You keep ISIs as small as possible for efficiency and scalability of the network. Whereas BGP carries your customer prefixes, your internet prefixes, and of course the EGPs are independent of ISP network topology. Hierarchy of the routing protocols. OSPF ISIs is the IGP. We talk BGP to other ISPs. We talk BGP at exchange points. We talk static or BGP to our customers. And because BGP customers need to see the internet, we need to run BGP on top of ISIs in our backbone. So that's why we have ISIs and then IBGP sitting on top. Okay, so choosing an IGP, I've given you slides comparing OSPF and ISIs. Pick one that works for you. So pick one that works for you. I won't really recommend. We did ISIs in the workshop. As you'll see, it's actually quite easy. It's quite easy. It's more secure than OSPF because it runs on the infrastructure. OSPF runs on top of IP, so you can attack OSPF using IP. And the other thing with IPv6, you need to run two separate OSPFs. One for OSPF IPv4, and the other OSPF for IPv6. Whereas ISIs, you just run one protocol, two topologies. So ISIs is a lot more sensible, for me anyway, than using OSPF. Keep the routing table as small as possible. If you can count the routers and the point-to-point links in the backbone, those are the IGP entries you should have. So even for sizable networks, your ISIs will be nice and small. So router loopbacks, backbone mount point-to-point links, and network of addresses of any lines having an IGP running on them. use inter-router authentication. I mean, even though ISIS runs on the infrastructure, as you saw in the lab, it was quite easy to set up authentication. So may as well use it. It stops accidents from happening. If you're using OSPF, use authentication there as well. Summarization, if you can, it will help reduce prefixes in ISIS. More recommendations, use IP and number on customer point-to-point links. If you need a customer point-to-point link, put it into BGP instead. Don't carry it in ISIS, because that way you can keep ISIS small. BGP can carry lots of prefixes. Try and use contiguous addresses for the backbone WAN, and then summarize wherever you can. Don't summarize router loopback addresses, because IBGP needs those for the next hop. And finally, use IBGP for anything which doesn't contribute to IGP. So things like internet routing table should be in IBGP, customer addresses, customer point-to-point links, any broadband, dial-up, whatever, pools. None of those need to be in your IGP. For BGP, use neighbor authentication. We showed you how to do that. Use peer groups. It speeds up configuration efficiency, less chance of making errors, and so on. Communities, I haven't had time to show you, unfortunately. Communities make doing policy much easier. Use the route reflector hierarchy. I've told you about that. Showed you how to design it in this presentation in the POPs. Use route reflectors, it means your BGP will scale. For security, when we look at the infrastructure security, the network security, I have to point out that security is not optional. As a service provider, network operator, you have to protect yourself. You're the target. You have to protect your customers from the internet. Your customers assume that you know more about security than they do. You have to protect the internet from their customers as well. You don't know what your customers are up to. They could do something that is bad for the internet. And the thing is, if something like that happens, you might end up being the receiving end from other people. I've only got general recommendations here. We could spend a week doing a security workshop. But typically for router security, usernames, passwords. Don't just have admin or something like that as the access. Every single person who accesses the router, give them a username, because then you know exactly who's logging in. You have a proper audit trail of who's logged in. If you just have a generic admin account, you have no idea who uses it, no idea who's got the password. So make sure you have usernames and passwords for every single user. Put filters onto the access, the VTY ports. When you telnet or SSH to the router, put a filter there that limits who can SSH. Generally what ISPs do is they have trusted hosts in the NOC, and it's only those trusted hosts and the backbone routers that can get access to each other. You don't want the public internet to be able to get any response from your router, so blocking access from the rest of the world, very important. Also, use TACAX. TACAX is a server that runs on a Unix system that hands out hands out passwords when people log into routers. You log into the router, it asks the TACAX server for what the password is. It's a secure link between the router and the server. Actually, it doesn't ask for the password. It compares strings of the password, so the hash of the password you entered versus the hash of the password stored on the server. Okay? So it's centralized authentication. It means that if you need to add a user, you add it to TACAX server and you immediately get access to the router. If you need to remove a user, you just remove them from the TACAC server database and they no longer have access. If somebody leaves your company, you can simply remove them from the TACAC server and they no longer get any access. If you store the enable password on the TACAC server, you want to change it, you change it on the server, and then it's automatically changed on all the routers everywhere else. So it's a very good way of quickly making changes for router security. Don't use Telnet. Use Secure Shell, and make sure your Secure Shell has a good, strong key. You need to use 2048-bit or higher now modulus, otherwise the smaller ones can be quite easily attacked. So use Secure Shell, don't use Telnet. VTY filter should only allow the NOC access, don't allow any access from outside your network or from your customers. Denial of service attacks. You need to be able to deal with those. So the best way, well, denialinfo.com, don't know if it's still there, I think it is. Dealing with things like remote trigger black hole filtering. So if a customer of yours is attacked, or you want to block access to a particular site for some reason, you need to install a remote trigger black hole setup on your backbone. Have a look at the Team Cymru website to find out how to do that. You can find links starting off from here. Make sure you've got effective filtering on the border routers. There are quite a lot of things happening that you should not allow into your network. Things like Microsoft NetBIOS. You see a lot of that. That should be running on the public internet. There are lots of viruses, worms, DOS attacks on routers and so on, testing various ports for vulnerabilities, usually on Microsoft Windows. You need to block those at the edge of your network. Very important to do that. Static customer connections. I talked about unicast RPF on Tuesday, wasn't it? Make sure all your static customers have RPF on the interfaces. And that way, you stop them sending packets apart from those you are expecting. Network Operations Center, make sure it's protected as well. Generally what ISPs do, you have SSH access into a Bastion server in the NOC, and from that server you can access the routers and everything else. So when you're traveling, you need to log in to your network to do maintenance, log into that one machine, all it runs is SSH, and then you can go from that machine to others in the network. Make sure the corporate network is behind a proper firewall. Okay, that's quite important as well. So as I said, your customers should not send any IP packets out to the internet with a source address other than the address you have allocated to them. That's what the RPF check on the interfaces will actually do. Now, out-of-band management. This is important as well. Out-of-band management is not optional. This gives you access to network equipment in times of failure. For example, here in the lab, you have been accessing the routers out of band. You haven't been telnetting to the routers, you have been telnetting to a fake access server that gives you access to the console of the router. That's what I mean by out-of-band management. You're not going across the network, you're going into the router console. But you're doing it from the comfort of your office, or home, or wherever you are. This ensures quality of service to customers, minimizes downtime, minimizes the repair time, and eases diagnostics and debugging. So, typical example, you get an access server, put a modem onto it to let yourself dial in. If it's a remote site, quite useful to do that. The console ports of all network equipment is connected to the serial ports. So you take all the consoles of the routers, plug them into the access server. You then telnet to the access server, and it will map you through to the console port. And this gives you full out-of-band access. So it looks like this. You've got the routers here, You got all the console ports connecting to an access server. You can then telnet or SSH to an access server, maps you through to a console port that you can then use. Right? So it gives you console access to your routers without going into the data center. So that means you stay warm, you can stay in your office, and you can manage all the equipment if you lose IP access. If it's a remote site, you could probably put a modem onto the access server, so you can dial into the modem and then get access to the network that way. If you break the whole connection, you can still dial in and fix things. Statistics gathering also happens in the out-of-band network. So routers using NetFlow, syslog is enabled. The thing is, the management data is all sent by UDP. So it can be congestion and failure sensitive. So this ensures that management data is not lost at the time the network is being congested. So this gives you maximum information under all circumstances. So again, watch your statistics gathering. Gather syslogs, system logs, NetFlow information, all that kind of stuff you want to capture in the network. Final piece, the test lab. It's very important to test things. It's not a good idea to try out services on the live network. So you want to build something that looks like a point of presence, keep some routers to the side so you can try out new services or new configurations. Actually, with the Dynamips that we're using here for the workshop, this is actually a very powerful tool to let you simulate or test your network infrastructure configurations. So more ISPs are now using Dynamips to test new configurations. And it lets you find and fix potential problems before they go into the network. So how do we do it? Some people will dedicate equipment to the lab. Other ISPs, they're always buying routers, so they just buy routers in advance, 3 months earlier than they need them, and they can put those in the lab for testing. Other ISPs use lab equipment as hot spares. So rather than buying a 24/7 break-fix contract from the vendor, they just buy a break-fix. So if things break, you send it back to factory and get it fixed. They buy extra equipment and they leave it running in the lab. If something breaks in the network, they take equipment out of the lab, it goes into the network, and they send the other part back for repair. The vendors don't like you using this because they can't sell expensive maintenance contracts. But an expensive maintenance contract won't fix your network faster than you. If you can take the hardware out of your lab into the network, it usually means walking from one room in the data center to another room in the data center. You can fix it in a few minutes. Your vendor probably has to drive from their office. They're going to come and look and see what's wrong. Even if they say 4 hours break fix, that's not enough, right? It's too long. If your network is broken, it's much quicker to go next door to the test lab, pull out the line card, put it into the router that's broken, and back it comes, probably having no more than 2 or 3 minutes downtime. Okay? We did that at UNet. Our lab was full of hot spares. We just had a break-fix contract. We did not have a 24/7. Cisco didn't like us for that, but too bad. They could not give us a 5-minute guaranteed fix time of something if hardware broke. Can't afford a test lab? Set aside 1 spare router and server to try new services. I should add it here, use Dynamips. Use Dynamips as it's running on this thing, because you can try out configurations and so forth before you even put it onto the network. But never try out anything new on a live network, because things will seriously break. Operational considerations. Why design the world's best network when you haven't thought about good operational practices? So the first one, maintenance. Never work on a live network, no matter how trivial the change may seem. Establish maintenance periods that your customers know about. Tuesday 4 to 7, Thursday 4 to 7 is very typically used in the industry. Tuesday 4 to 7 a.m. means you spend Monday getting ready. Thursday 4 to 7 means you can spend Wednesday getting ready. Whereas if you try and do Monday 4 to 7, you work the weekend. You do Friday 4 to 7, you probably have to work the weekend fixing things. Right? So maintenance never happens on Fridays or Mondays. Tuesday and Thursday is very, very common in SP networks. Differentiate between customer support and the network operations center. The network operations center runs the network. Customer support supports your customers. Different people. Customer support fixes customer problems. NOC deals with the backbone and internet. If customers complaining about internet problems, they phone the customer support. Customer support passes on to network operations. Different thing. Network engineering are the people who design the actual infrastructure. They're doing the next generation, they're trialing new services, new routing design, new things. They should not be doing customer support, right? Network engineers do not talk to customers. Customers talk to customer support, that's all. Even network operations does not talk to customers. Network operations talks to other ISPs and to customer support. You need to keep this separation between the three parts of the organization. Even if they're three different people. If it's a small organization, 3 people, it has to be very clear that customers speak to customer support. Network Operations Center deals with the running network, peers, transits. Network engineering designs the next generation. Communications with the NOC. You need to know the contact details for NOCs in your upstream provider. Right, so your Network Operations Center has to have very good relations with your upstream. If you don't have good relations with your upstream, you cannot fix anything. There is a telephone system, voice over IP, called the INOC DBA. You can use that. Some people are using that one. Only network operations centers can use that system. So at least if you make phone calls on that, you know somebody's going to answer and is going to be a network engineer. Design summary of this. Keep it simple and stupid. So that's what to remember. Keep the network design simple. Keep the network design stupid. Don't build complex network. If it becomes complex, it becomes very, very difficult to run. Redundancy is important, security is important, also make good use of the technology that's available. Make it easier for yourself. Above all, ensure quality of service for your customers. Okay, that's the most important thing. That's really all I have to say, ISP design. Okay. So it goes over some of the important things. I mean, some probably apply less to you than they do to other folks. It all depends on the size of your network, but it is important to pay attention to how you design your network, the best way of scaling it. Because if you start with just a random mess, things connected to each other, it just gets very, very complicated to try and run. And so we want to try and keep things as simple as possible. The presentation is based on what I've seen a lot of ISPs doing. It's not made up. And again, any ISP I help or have worked with over the years, I've pushed them in this general direction so we can get a nice, scalable, simple design for the network.